Welcome friends to the another session on transistor amplifier. In this session, we'll be discussing about the transistor biasing circuits. In the earlier session, we have seen what is transistor biasing, what is the DC load line, and what is the Q point of the transistor. Now in this session, we will see how the transistor bias can be achieved by using different circuits. So in this session, we will see the different types of transistor biasing circuits, their working, their analysis, and their advantages and disadvantages. And we will see what is the best circuit that can be used for biasing a transistor when we want to use transistor as an amplifier. As you know that you are viewing this session on my YouTube channel, Learn with Prakash Kanade, and don't forget to subscribe to the channel. As we know that transistor is a three-terminal device, and whenever we want to use any transistor in any electronic circuit, then we need to provide appropriate voltages to the emitter, base, and collector terminal of the transistor. When we provide these appropriate voltages to the three different terminals of the transistor, then that is being called as a biasing. You will find that there are different biasing circuits. Say for example, we have a circuit which is being called as a fixed bias circuit or base bias circuit. Another circuit is the base bias with emitter feedback. The third type of the circuit that is being used is the base bias with collector feedback. And the most popular biasing circuit is the voltage divider biasing circuit. So in this session, we will discuss all such four different types of biasing circuits, and we will see what are the advantages and disadvantages of using these circuits. So let us first of all go to the circuit, and this circuit is being called as a base bias circuit or fixed bias circuit. You will find that this circuit is one of the simplest type of circuit. Suppose this is our transistor, this is the emitter terminal, this is the base, and this is the collector terminal. The positive VCC DC power supply is being applied through the resistance RC to the collector. The voltage between collector and emitter is called as VCE. Emitter terminal of the transistor is grounded. Observe that the base terminal of the transistor is connected to the resistance RB, and the other terminal of the resistance RB is connected to the positive VCC. And the voltage between the base and emitter terminal is being called as VB. So you will find that this is the simplest type of biasing circuit. By using such circuit, we can apply appropriate voltages to the base, emitter, and collector of the transistor. We can adjust the values of RB and RC in such a way that the Q point of the transistor will be at the center of the DC load line. If you go for the analysis of this circuit, then from this circuit we can easily find out the value for the collector current which is flowing through this resistance RC. You will find that at one end of RC we have VCC, and at another end of the RC there is VCE. There is another way to compute this current IC. Say for example, at this point we are having the voltage VCC, and this is the voltage between base and emitter is VB. And we know that current IB will be flowing through the resistance RB. Therefore, IB can be calculated as VCC minus VB divided by RB. And we know that the collector current IC is IB into beta. And therefore, we can calculate the value of IC is equal to IB into beta, where IB is equal to VCC minus VB divided by RB. So this is the simplest way by which you can calculate the collector current of this transistor. So as I said, the base bias circuit is one of the most simplest type of the circuit, and only resistance RB is being required and another resistance RC is being required. So we require only two such resistances. By using this circuit, you will find that we can easily set the biasing conditions and there will be no loading effect, as you will find that the no resistance is being present in the base emitter junction. So these are the advantages of using base bias circuit. But you will find that there are certain disadvantages as well. You will find that this circuit has a poor stabilization. This is because when the circuit is operated over a long period of time, then the heat will get developed and the development of the heat cannot be stopped in this circuit. This circuit has a stability factor which is very high. Now we require a stability factor to be low, but this is a circuit of which the stability factor is very high. Therefore, there are strong chances of thermal runaway. So we know that due to the thermal runaway, when the collector current increases, the power dissipation increases. When the power dissipation increases, it again further increases the collector current. And the transistor goes on heating continuously. And therefore, you will find that the thermal runaway must be avoided. But in this circuit, there is no arrangement by which the thermal runaway can be avoided. And therefore, this circuit you will find that very rarely used for the transistor as an amplifier. Now there is another circuit. We can make some modification in the base bias circuit. And this circuit is being called as a base bias with emitter feedback. The circuit diagram for the base bias with emitter feedback is as shown in the figure. This is our transistor. You will find that here what we have done is that we have added a resistance RE to the emitter. In the earlier circuit, you will find that the emitter was directly grounded, but now in this circuit we have added this resistance RE. The RC is there, RB is there. RC is connected between positive VCC and collector. RB is connected between positive VCC and base terminal of the transistor. The voltage between collector and emitter is called as VCE, and the voltage between base and emitter is called as VB. The current flowing through this resistance RE is being called as the emitter resistance RE. The base current IB flows through the resistance RB, and the collector current IC flows through the resistance RC. Now this is also a simple type of circuit. The only thing is that here we require 3 resistances instead of 2 resistances. So one additional resistance is being used. And you will find that the voltage across this resistance is being fed back to the input, and therefore this circuit is being called as a emitter feedback circuit. Now we can adjust the values of RB, RC and RE in such a way that we can have appropriate base voltage, collector voltage and emitter voltage of the transistor when no AC input is applied. And we can adjust these values in such a way that at the DC load line, we can set the Q point or the operating point of the transistor at the center of the DC load line. So this can be easily achieved, and therefore this circuit is a biasing circuit. We can analyze this circuit. Suppose the maximum value of collector current we need to find. This value is being called as a IC saturation value. Now, since this is the maximum value of collector current or saturation value, you will find that this voltage VC will be equal to 0. And therefore, IC saturation can be given as VCC divided by RC plus RE. So this is the equation for the IC saturation. Now, if you analyze this circuit, then we can find easily the expression for VCC, as VCC is equal to, VCC is the voltage between this terminal and the ground terminal. Therefore, we can say that this is the voltage which is equal to IB into RB plus VB plus IE into RE. Therefore, this equation is being written, VCC is equal to IB into RB plus VB plus IE into RE. But we know that IB, the base current, is equal to IC collector current divided by beta, or beta IB is equal to IC. And IE and IC, that is emitter current and collector current, they are almost same. And therefore, we can rewrite the above equation. VCC is equal to IC into RB divided by beta. So IB is being replaced by IC divided by beta plus VB plus IE into RE, but IE is being replaced by IC. So we have arranged this equation in such a way so that we can get the expression for collector current IC. So collector current IC will be equal to now VCC minus VB. This VBB will go on this side divided by RE plus RB divided by beta. VB is the base to emitter voltage. This voltage is very small compared to VCC, and therefore we can neglect this base to emitter voltage, and we can rewrite this equation as IC is equal to VCC divided by RE plus RB divided by beta. So if you know beta, then you can easily compute the value of IC. Similarly, in this circuit, if you want to compute collector voltage or collector to ground voltage, then we can easily compute it as collector to ground voltage. So collector to ground voltage means voltage between collector terminal and ground terminal. So this is just nothing but VCC supply voltage minus the voltage across the resistance RC. Therefore, VCC minus IC into RC. Similarly, we can compute emitter to ground voltage. So emitter to ground voltage means the voltage between emitter terminal and ground terminal. So this is the voltage across the resistance RE. Therefore, it can be written as IE into RE. But IE and IC are almost same, and therefore it can be written as IC into RE. And it is also possible to compute the K beta factor or beta sensitivity factor of this. And this can be written as 1 divided by 1 plus beta RE divided by RB. So you will find that this circuit has a certain advantages. This circuit has an advantage that its operating point is more stable against the changes in the temperature or beta value. Now, if there is some change in the temperature or beta value, then you will find that the voltage across the resistance RE will increase, because when collector current increases, the emitter current will also increase. And when the emitter current increases, the voltage across the RE will increase. And therefore, it will cause an impact on IB. That is, IB will decrease. And when IB decreases, you will find that automatically the increase in the IC will be compensated. And therefore, this circuit has an advantage that its operating point is comparatively more stable against the change in the temperature or beta value of the transistor. But when the beta value is fixed, then you will find that we need to keep RE very high, or we need to keep RB very low. If we keep RE very high, then a high positive voltage or high supply voltage is being necessary. If we keep RB very low, then you will find that you need to use a separate source for the base and collector. That is, in the same circuit, you need to use two different sources, one for the base and one for the collector. And this is practically not good. Also, you will find that when the resistance RE is used, then this resistance RE is actually a feedback resistance, because this resistance has an impact on the input base current. And therefore, this feedback is a negative feedback. And therefore, it ultimately reduces the gain of the amplifier if this biasing circuit is used in the amplifier. So these are the certain disadvantages that we have with emitter feedback circuit. So later on, some modifications were made, and we have another type of the circuit. And this circuit is being called as a base bias with collector feedback circuit. Now, the change is a slight change is there in this circuit. You will find that instead of connecting this resistance RB to the positive VCC, here what is being done is that resistance RB is connected between collector and base terminal. So when the collector is connected back to the input, that is to the base terminal of the transistor, then this is a feedback, and this feedback is being called as a collector feedback. Resistance RC or RL is the same as in the earlier diagrams, and resistance RE is connected between emitter and ground. So you will find that the current flowing through this resistance is IC plus IB, of which IB will flow through the resistance RB, and IE is the flowing through the resistance RE. Now, when we analyze this circuit, we can easily find out the value of the highest value of the collector current IC saturation, and this will be VCC divided by RE plus RL. So when the transistor is in saturation, then VC is equal to 0, and therefore the highest value of the collector current will be VCC divided by RE plus RL or RC. Now, there is a actual value of IC even can be found by using this expression. We can say that IC is almost equal to VCC minus VB divided by RE plus RC plus RB divided by beta. A similar expression that we have obtained in the earlier analysis also. So here we have analyzed the circuit via RB because we do not want to use VC because VC is unknown many times, and therefore we can compute the value of collector current by using this expression. Similarly, it is possible for us to compute the value of collector to ground voltage VC and emitter to ground voltage VE. So VC will be VCC minus IC plus IB into RL, or if you say neglect IB because IB is very small in comparison with IC, and therefore the same expression can be written as VCC minus IC into RL. And VE means emitter to ground voltage. So emitter to ground voltage is just nothing but the voltage across this resistance, and this voltage can be find out IE into RE. But IE and IC are almost same, and therefore this expression can be written as IC into RE. Collector to emitter voltage VCE is just nothing but VC minus VE, and therefore by substituting the value of VC and VE, we can get the expression for collector to emitter voltage, this voltage, collector to emitter voltage, and this will be VCC minus IC into RE plus RL. So this circuit again has advantage. Here also we are using a collector feedback, a negative feedback is being used. Therefore, whenever there is some rise in the temperature or whenever there is some change in the beta value, then you will find that this change will be compensated, because when collector current increases, then the voltage drop across the resistance RSC or RL will also increase, and therefore you will find that it will cause an reverse impact on the base current IB, that is IB decreases. When IB decreases, then you will find that it ultimately compensates the increase in IC. But this circuit has certain disadvantages also. You will find that in order to work this circuit properly, we need to keep this RC very large, or you need to keep RB very low. If you keep RC very large, then you require a high value of battery, that is VCC. If you keep RB very low, then you will find that the voltage across the base and collector junction will be very low. So this reverse voltage will be very low. And also you will find that since RB is used between collector and base terminal, it is causing a negative feedback. And because of this negative feedback, the gain of the amplifier will get reduced when such biasing circuit is used in amplifier. So the most popular circuit that is being used for the biasing of the transistor, and it is being called as a voltage divider biasing circuit. This is the circuit diagram for voltage divider biasing circuit. Here you will find that we have used this resistance RC for the collector terminal, RE for the emitter terminal. And instead of using RB, what we are doing is that here we are using a potential divider resistances R1 and R2. R1 is connected between positive VCC and base, and R2 is connected between base and ground terminal. So this, since in this circuit we have been using the voltage divider resistances R1 and R2, and because of this you will find that this circuit is being called as a voltage divider bias circuit. Now in this circuit we can easily adjust the values of R1, R2, RE and C, 4 resistances, in such a way that we can set the Q point at the center of the DC load line. We can analyze this circuit. We know that the voltage across the R2 can be given as V2, and it is VCC into R2 divided by R1 plus R2. Then the voltage across the emitter terminal VE can be given as V2 minus VB, because if the voltage at this point is V2 and the base to emitter voltage is VB, then the difference of this is the emitter voltage VE. From this we can calculate the emitter current I, VE divided by RE, that is V2 minus VB divided by RE. If we neglect this VB in comparison with V2, then we can say that the emitter current I is V2 divided by RE. Also, we can say that the collector potential, that is the potential between collector and ground, can be given as VCC minus IC into RC, because this is the voltage VCC, and we need to neglect the drop. We need to subtract the drop across the resistance RC. And collector to emitter voltage can be given as VC minus VC. Collector to emitter voltage means the voltage between collector and emitter terminal of the transistor. So we can substitute the value of VC and we can substitute the value of VE from the above expressions, and we can get the value of VC as VCC minus IC in the bracket RC plus RE. So the highest value or the saturation value of the collector current can be found by using this formula VCC divided by RC plus RE. Because in this case, you will find that this voltage VCE will be almost equal to 0. And the beta factor can also be determined by using this formula. K beta is equal to 1 plus beta RE divided by R1 terminal R2. So this circuit is a very popular circuit. So this is the advantage of this circuit, that this circuit has a tendency to stabilize the operating point against any change in the temperature or beta value of the transistor. You will find that in the analysis of this circuit, nowhere the beta value appears, and therefore all the expressions are beta independent. Also, you will find that in this circuit we have used the feedback by using RE, and therefore you will find that this circuit can compensate any change in the temperature or beta value. Also, you will find that the stability factor of this circuit has an ideal value, and this ideal value is 1. And therefore, you will find that this is the most stable circuit, and hence it is most commonly used for the biasing of any transistor amplifier. There are certain disadvantages also. You will find that in order to satisfy the working of the circuit, it is necessary that you can keep RE very large, or you can keep R1 parallel R2, the voltage divider resistance, very low. So neither we can increase RE very large, nor we can keep this very low. So we need to compensate somewhere in between. Because if we increase the RE very much, then you will find that the high value of VCC will be necessary, and therefore we cannot increase RE very high. So friends, these are the 4 different circuits that we have seen. We have seen that there are some minor changes in the circuit configurations or in circuit connections, but you will find that their working goes on changing even if you change one component, even if you add one component, or even if you remove one component from the circuit. Out of these 4 circuits, as I say, the voltage divider bias circuit is most popular, and in many amplifier circuit you will find that this circuit is being used for biasing of the transistor. Friends, thank you viewing for this session. If you have any queries, then you can write to me, or you can ask these queries during the oral discussions. Thank you all for viewing the session.